all over the place, and perhaps even slides. Huh, that's fun. Okay, great. So yeah, hi, I'm Gautham Narayan. I'm giving this talk on behalf of the ANTARES team, which is based mostly at NOAA Lab, along with a few of us in Illinois. And Konstantin Melanchev, my postdoc, is now a Link Fellow at CMU. So I think the key challenge that we've outlined here is not that these big surveys are producing petabytes of data over a 10-year timescale, but that data has to be useful to the entire community. And you saw this nice slide from Francisco showing you the different use cases for real-time data. And for us, making real-time data useful really means processing heterogeneous sources of data, so not just LSST, in real time, period. So what do we need to do that? Well, you need something that can actually sift through all of the different data streams from all of the different experiments out there. You, like people have said, need to be able to characterize and classify events, identify outliers. That was an important theme yesterday. We do need to figure out how to prioritize these events for follow-up. What gets VLT time? And then we should also be providing observers with the tools to actually make that follow-up happen. And ideally, improve as we get more and more data. All of this has to happen while handling 10 million alerts per night, which we're not going to go look at a web page to do. So you need to have some kind of search capability and filtering capability and compute. So Antares is really designed to manage this. This is the rogues gallery of all of the people involved. And to sort of give you the layout here, Antares is a broker system that takes in alerts right now from LIGO and ZTF, as well as ultimately from LSST. And it's doing all of those tasks that I mentioned. And one key distinction between it and some of the other brokers is that rather than us building algorithms to classify the stream, you build the algorithms. We run your code on our system. So in other words, you define your science, we make it happen. All of this system is live. It is active on ZTF. It is deployed on the entire the Google Cloud Platform. So we use Bigtable, for example, for our database system. Everything is containerized. There's provenance tracking. It's all open source. You can download everything. There's even documentation. And this flexibility of cloud hosting really allows us to do a lot of testing at Rubin scale. It leaves us the ability to have large archival catalogs and write these nice custom filters. We're actually also providing Rubin's own internal alert filtering service to the community. So rather than step you through my slides, I'm going to just do a demo and show you how this entire thing works. So I'm not logged into Antares in any way, shape, or form here. This is just the front landing page. And yesterday we talked about, for example, finding TDEs and AGN. I just mentioned those custom catalogs. They're all listed here. And you might say, well, what the heck is an AGN and how is it different from a TDE? I could, for example, go click on Veron and say, well, that has a list of AGN there. And I know that TDE in particular may, for example, show up in post-starburst galaxies preferentially. So I could click multiple catalogs. This is a little tricky to do with the microphone. So, and then I can just ask for alerts within, how about the last week? Okay. No magic here, just 2 catalogs selected, and I'm going to apply my filters and see what I get. Take a second, but hey, there you go. Click on one of these things, give it a second. That's an AGN light curve. That didn't take any time at all to set up to do, right? And we have a lot of these filters, including now all of PS1 3Pi survey detections. So you can write complex search queries very, very easily to find interesting objects that Antares has seen in the stream within any time window. You'll actually hopefully also notice on the main page, there's a way to search for filters. I'll talk about the tags, but there's also a search box here for gravitational wave event ID. So you could, for example, take a LVK ID, stick it in there, and get everything that has alerted in, say, the last 2 days, potentially in the same search region. So that is one way to answer Dr. Temple's science case from yesterday. But you can do more than just that. Like I said, Antares lets you run your own code. And what we've talked about here is characterization and classification. So what we're really trying to do is not the needle in the haystack problem. That's easy. You just burn a haystack. What you're trying to do is find one needle in a stack of a whole bunch of needles that look very similar to it. So how do you do that? Well, you write filters. Filters are your own Python code. You develop these things. There's a nice Jupyter Notebook environment that will help you get yourself set up. I can show you that in a second. So Antares is connected up with NOAO's Astro Data Lab. This lets you develop your filter fairly quickly. You upload your filter back into Antares under this little filter tab at the top, and it just runs and provides things for you. So one of the filters that I'll talk about in a second is this thing called LACE that my grad student Patrick Aleo wrote. This is an anomaly detection filter, which is why I'm going to show it to you. So LACE is looking at not just the light curves of objects, but also their host galaxies and trying to find things that are both similar to other sources in its database, but also different. And rather than, maybe I'll show you the slides for this one. So LACE, like I said, takes the light curve information and host galaxy information and then builds this into a multidimensional latent space. And it's essentially tossing any normal common transients. We use a similarity algorithm called ANNOY from Spotify. This is what Spotify uses to recommend a song once you're done listening to Taylor Swift or whatever. And it's great at finding all sorts of unusual objects that look different from other sources. So for example, here's this weird double hump supernova. And LACE does all of these things and shows them to you in real time. My group does this. This is my own Slack on the Young Supernova experiment. And you can see a little LACE AD bot has been sending me transients until the last few days when ZTF started cryocycling their camera. And so it's a pretty good supernova of some sort that it's identified with a nice slow decline, which is cool. And you can see that that tag that it's added here is available along with everything else. So you can actually select, again, just like you did with multiple catalogs, you can select multiple filters, things that pass multiple people's criterion. That's, again, an incredibly useful feature. LACE also lets you do a similarity search, like I said. So for example, if I were really trying to find type 1a supernovae, I didn't actually need to run like a salt 2 fit on every single object that comes in. I could just ask for objects that are similar in the latent space. We do this. Turns out that type 1a supernovae look a lot like each other. So that isn't one object. That is several different objects all overlaid on top of each other. One is a reference, and then we just found the nearest neighbors in the data set that look identical. Not just because the light curves are similar, but because the host galaxies are similar. And of course, if you could do this in a one latent space, you can do it in a reduced latent space. You can ask for things that have similar host galaxies, but different light curves, or vice versa. And so this is all useful. You're using contextual information. And of course, all of those features, all of that contextual information means that you can do real-time compute at scale. Everything is in Antares' own database. So you can effectively write an SQL query that says, give me all of the features computed by any number of filters and search for a whole bunch of objects, identify light curves, all in real time. Every single night you get alerts from LSST, you can rerun your notebook and redo this analysis. You don't have to wait for an LSST data release. You don't have to wait for DR1. And so this all works right now in Astro Data Lab. And of course, if you have all of this data sitting in a database, well, we might as well give you a Python client to have access to it. So Antares has a Python client. Every little page on Antares is actually on the top. For example, if I go back to the front page, you'll see a little API access button here. It tells you how to get access to absolutely everything in our database. So you can, for example, in this case, as you select an extra tag or something, it's updating the query that you have. And so you can run this query in your Python client, connect it up with your pipeline. This is cool and useful. And the reason it's cool and useful is that you can start to connect it up and do even more complex things. So Antares' Python client is sending you is just receiving Kafka messages, you can also use the Sima hopscotch client to listen to that. But then you can take that and then trigger the LCO Tom toolkit, which Tim Lester will tell you a little bit about, or Aeon and the Gemini queue, which you'll hear about from Brian Miller. This real-time Tom integration is great. You can either do this again through the Python client or a Jupyter notebook, or the Tom plugin that already exists for Antares. So it'll query the service and you can trigger follow-up fairly quick. We've done that multiple times. We've gotten several interesting spectra. We actually have a program now going with, among others, Emily Ishida in this room and the folks who are working on Foremost, including Isabel Hook. We're calling this Respect Within Desk. The idea is, as you find rare objects with things like anomaly detection, your AI can get significant improvements every time you tag a new object. This is active learning. And if we can find more and more of these objects, then we can trigger follow-up in essentially real time, or about 15 minutes, because that's how quickly LCO recalculates its queue. And we are doing this. Amanda Wasserman, who's a grad student, is now at LBNL this semester working on it. We've gotten spectra. Amanda worked with a REU student, Henna Abuneme, last summer to do this. And we were able to identify AGN and supernovae. And Henna was looking at spectroscopic twins. This is Amanda next to everybody's favorite telescope in Chile at the La Serena Data Science Summer School last summer. She's, like I said, now just starting at LBNL to finish up building this and integrate it into Antares. It'll hopefully give us more of these science papers. We've got lots of collaborations with existing groups. Do I have one more minute or no? Okay, so I wanted to quickly finish up with some of the MMA stuff that we can do. We've been talking a lot about LSST here, rightfully so, but surveys don't operate in isolation. In fact, if you look at follow-up for GW 1908-14, which is the less famous counterpart to GW 1708-17, which might have been a BNS merger, but we'll never know because these surveys didn't coordinate with each other. In 2019, they all took images of roughly the same area of the sky over and over, ignoring many of the regions of high probability space. So really what you want to do is have a broker system that can handle multiple streams and coordinate data together. You want to identify the rare and fast sources early, like I've been talking to you about, but then actually communicate to the entire community. So this needs this integrated ecosystem. This is the goal of the SIMA project that I'm the PI of. The idea here is if we find something like a kilonova with a gravitational wave signal, we send out an alert over a system called Hopscotch. And that can update things like the gravitational wave treasure map, show you where the sky area is. We can start taking in alerts from NASA missions like SWIFT or IceCube, update those. So SIMA serves IceCube and LVK right now. And then as the kilonova gets brighter and we start to see Rubin alerts that come out a few hours later, we will also be able to update all of this together. All of this is connected up with this ecosystem, with the Tom toolkit, with Aeon, with the treasure map, so you can trigger your follow-up and then report your results with another service called Hermes that Brian will tell you more about. So Francisco showed you his ecosystem diagram, and here's where my boxy diagram differs. His thing was very linear. I don't think we live in a linear world. I think we have an interconnected web of services. And that's the key ecosystem that we're trying to build. Every facility connected to everything else, no longer siloed, allowing real-time time domain science. That is an exciting thing, and I think we should all come play with it. It's mostly exciting. I'll stop there.